Hello chemists, this video is going to be about how to use Ka values to calculate pH of solutions, which is basically what we want to be doing with them in the first place. Ka, as a reminder, is an experimental value. It is not something that is observable about a solution. It's something that is comes out of a relationship between a couple of different things. So it is something that was determined experimentally for given acids. Okay, so continue to remind you, in water, weak acids will dissociate to form hydrogen ions / H3O plus. Basically what happens is you've got your hydrogen ion come off and that immediately forms an H3O ion with water. So basically we use them interchangeably, the same as each other. And it's conjugate base, which is whatever's left over after the hydrogen comes off. And we write that like this. We've got the HA, that's the acid. We've got the A minus, which is the conjugate base. HA is hydrogen and then an acid. A minus is just the acid. Hydrogens come off and it's left a negative charge. That hydrogens come off goes onto the H3O there. HA is the acid, A minus is its conjugate base. And you can write that dissociation right here. This is all revision of my last video, just kind of making sure we're all on the same page. As always, we've got the reactants minus water on the bottom and the products on the top. Concentration. Okay, so we've got these equations here. The dissociation constant can be written like this. And when we're talking about acids, we use Ka instead of Kc. It's the same thing. Ka just means we're dealing with an acid. Okay, ready to get into it? Let's go. All right, so consider a 0.01 mole per liter solution of ethanoic acid. Ethanoic acid being CH3COOH or vinegar. We've got an equation here, CH3COH, that's our AH, plus water, is in equilibrium with CH3COO minus, which is our conjugate base, our A minus, and H3O, which is where our hydrogens went. And the Ka of that whole equation is 1.7 times 10 to the negative fourth. If we don't have that number, we can't go anywhere. But they're experimentally determined, and you can usually just look them up. They'll be given to you. Okay. First thing we want to do is find out the pH of that acid. That's our final goal. So in order to calculate the pH, we need to calculate the concentration of hydronium, H3O, because pH is related to the concentration of hydronium. All right, so in order to be able to do that, we have to make two assumptions, and they'll make our life easier. And these assumptions you'll like because they do, in fact, make things quite a lot easier. First thing is the concentration of CH3CO minus, the conjugate base, is equal to the concentration of hydronium. And there is no contribution of H3O plus from the water. So even though there is a little tiny bit of H3O plus in the water, as we discussed in the previous video, it's very, very, very tiny, so we can ignore it. And there's the same amount of CH3CO minus and H3O plus, because if we have 1 mole of the CH3COOH, and it splits apart, it'll split apart into 1 mole of CH3CO minus and 1 mole of H3O plus. So 1 mole of product gives us 1 mole of each of the two reactants. And the concentration of CH3COOH is approximately equal to 0.01 mole per liter because the degree of ionization is very small. Basically what they're telling us is the value of the concentration of 0.01 mole per liter, or sorry, the concentration of the acetic acid they gave us, the ethanoic acid they gave us in the question, is the concentration we're using. By the degree of ionization being very small, they mean there's nothing going on except for the acid chemistry. And we have to make those two assumptions, but it's good that we can make them because it makes our math really easy. Okay, so how to actually do it? All right, first thing we do is we're back to our assumption, CH3COH in equilibrium, blah, blah, blah. And we put this in our Ka equation here. This should be familiar from the other page. Ka equals CH3COO minus, rather, that's our A minus times H3O plus, concentration of both. That is just like we looked at on the previous page. And that is all over the concentration of CH3COH, that's our HA. So this is HA, this is A minus. This is our acid, this is our conjugate base. And that all equals 1.7 times 10 to the negative fourth. The only one of these we know right now is that one. and kind of know the other two, but I'll get to that. Using our previous assumption, we are going to say that the concentration of the conjugate base and the concentration of H3O plus are equal. So we get this here, H3O plus concentration times H3O plus concentration over CH3COH. Simplify that to H3O plus squared over CH3COH. Okay, now we're getting somewhere. Plug in our known Ka value from here, 1.7 times 10 to the negative fourth equals concentration of hydronium squared over 0.01, that's 0.01 coming from here. Okay, now that's just some math. We can do that. Shift the 0.01 over here, over to the left-hand side rather, square root, and we get the concentration of hydronium equals 4.12 times 10 to the negative fourth moles per liter. Awesome. Now we have the concentration of hydronium. Are we done? I've waited for all of you to chorus, no, Lindis, we're not done. You're not done. You have to do one more thing because you want to calculate not the concentration of hydronium, but the pH of a weak acid. Okay. Calculating the pH of a weak acid, same assumptions as before. Now we just need to throw it into our pH equation. So the pH is actually equal to the negative log of the concentration of hydronium. We now know the concentration of hydronium, so pH is equal to the negative log of that, which means that pH is equal to 3.38, which is pretty acidic. Not super acidic, but pretty acidic. So that's how you do it. It's basically a Kc equation, but we have to make a couple of assumptions, and those assumptions are the really important part. You're assuming that there's the same amount of CH3COH and H3O+, and you're assuming that the concentration given for the acid is the actual concentration that you use, which it is. That's it.